Hello. 1, 2, 3, testing. Okie dokie. All right, where am I? Am I here? Do I have... This should not be plugged in right now. This other thing should be plugged in. Let me wrap this cable up. And I have other stuff here. What do I have other stuff here? I think I'm good. Good morning. Excuse me. Let's try again. 1, 2, 3. Good morning, everyone, or good afternoon, or good evening, wherever this might find you. Hi, Erasto. Good to see you again. Welcome to a surprise live stream on Monday. I already told you, folks, this fall semester live streaming is going to be a little off all over the place. The sound is good. The sound is good. It's going to be all over the place because I have a lot of teaching, and so I don't know yet which day of the week I will be able to start streaming more consistently. Hey, hey, Victor. Yes, it is rare. It's a Monday stream, but that's because it's Labor Day here in the US, so it's a holiday, and shops are closed. I don't have to go to the office. There's no teaching, so why not, right? And Andres, good morning. ¿Cómo andas? So yeah, and also because I really want to get the advanced development in Grasshopper playlist out there in the wild as soon as possible. So the sooner we record the videos and the sooner we publish them, then the sooner people will have access to them and will be able to learn and put that learning to practice, and then the whole community will benefit from that, hopefully. So that's why I'm pushing it a little earlier in the semester. I also would like my students at the design school at Harvard to be able to benefit from all those playlists as well. So anyway, long story short, more recording, more publishing, and why not? All right. So thank you for being there. As usual, I love all of you, each one individually. And let's get started. Let me do, before the official diligence. No, that's not what I want. What is this? What is the window that I want? I want this one. I want my notes. I want my notes over here. Yes. So, all right. So just a few, as usual. Hi, my name is Jose Luis. I'm over there. This is Parametric Camp. We do live streams. Typically, we used to do them on Fridays, but until Christmas, it's probably going to be whatever day I have time to do this. So we go live. We do live recording of tutorials, which we then edit, copy, and paste, and we publish as polished videos, thanks to the help of fellows in the community, like Erasto, for example, who's on the chat right now and is helping me do a lot of this work. So if you want to know when we go live, follow us on social media. We're especially active on Instagram and Twitter. You can also subscribe to this channel, turn on notifications so that you get pop-ups and emails. And during the week, we have offline conversations in our Discord server. So you can join, you can say hi, introduce yourself, you can post questions, you can add suggestions for content. And on top of that, if you also want to know when we go live, we have a Google Calendar that you can subscribe to. I should put the calendar on the description of, right? No? Wait, can I put the join us? Blah, blah, blah. Exactly. Why not? If I do this and I say, wait, here. No, wait. So here, I'm messing with the description right now. Yeah. There you go. I put that and I put that. And that is a long. So can you see now in the description? Can you see the link to the calendar? right? Actually, yeah, I don't know why I never thought of doing that before. Is that true? Yes. And what if I do it on the next one? On the next one, I could do this and then just paste here the calendar description. Is that true? Yes. And then I see you. Can someone confirm that you can see the description? Sorry, not the description. Can someone confirm that you can see the calendar link on the description of this live stream right now? Yeah. All right. Thank you. Thank you, Rasta. Beautiful. Is it a long ass link or has YouTube shortened it to make it a bit more, a bit less intrusive? How does it look physically? How does it look? All right. Okay, and then here I'm gonna write myself a few notes of what is coming up today. Hi, thank you, Adita. Adi? Do you go by Adi? I have a bunch of friends called Adi. I have a friend called Adi who just published about a book called Cheese Dosa about his upbringing coming from India, but his upbringing here in the US. It's a lot of fun. I'm having a blast reading the book. Hockey dokie. Sent a screenshot on Discord. Whoa, let's check that screenshot. Why not? Ooh, all right, so it's shortened out. So that's great, actually. I like that. So beautiful. Okay, great. So shall we get busy? Less talking and more coding, right? So, okay, so what did we do? What did we do last time we met, which was 2 days ago? We did advanced geometry scripting. So we did a bunch of, so now we have to do a bunch of examples, which I wrote here. For example, so actually, why not? So we can probably advance this. We can probably advance this. I didn't want to do this. So what are we doing for examples today? So we're going to create, for example, a B-rep from a sweep. We're going to divide a curve in points. We're going to get a B-rep and we're going to get a bunch of UV points, right? So that's going to be super interesting. We're going to reparameterize a curve. That was a question that came up on the chat the other day. Was it Deepak who asked that? Deepak, are you here with us today? Deepak Tamilmani, are you with us today? Was it you or was it someone else? We're going to reparameterize a surface because, I mean, why not? And we are going to, you know what? And for this one, we're going to use default values of domain 0 to 1. Okay, and then for the surface also, and then this one, we're going to create a curve and we're going to create an interpolated curve through a list of points. For this one, we're going to use something that we haven't seen yet here on the, we haven't seen on the playlist, so people will not have learned that content yet, but we're going to offer it as a teaser because we will be learning about that very soon in a couple of videos down the road. So why not? Just give people a little bit of a teaser, right? All right, cool. So I think that's going to be it. And so let's get started. Any questions, concerns, suggestions, requests? I don't know, eyes? Open to all of those. So we're going to take, as you can tell, I've had a little bit of too much coffee this morning again. So, Nerve geometry. I'm making myself a folder here on And I'm going to pause this. And then I'm going to take this file. I'm going to take this file. I'm going to post it here. And I'm going to say, by the way, Arasto, since you're here, I need to show you. I need to give you access. We're going to start this new thing. We're going to give you access to a Dropbox folder where you can take the edited videos that I typically generate with your files. But you can take them, you can upload them, and then they will go into a workflow that I have to get the subtitles right away. So that's going to be super nice for us to exchange files. We'll talk about this. We'll talk about this on Discord. Nerves, geometry. All right. Because how is your internet in Japan? Arasto? I would assume it's pretty good. I would assume you have bandwidth to upload big files and stuff, right? All right. Okay. I love you, man. Thanks for being a dedicated P camper. Okay, so what are we? Are we P campers, parametric campers, campers? We need to. Hi, Michi, you're new here. We love new people. Welcome. How are you doing? If you don't know what you're doing or what we do here, feel welcome to rewind this video and start from the beginning, what I give the welcome speech. Anyway, so nerves geometry. So, and I said that we were going to start by creating a B-rep from a sweep. So to speed the process up, what I've been doing in the previous videos is that I was putting together the components. I think at this point, I would like to start doing that offline. So if we're going to start with a sweep, then I probably want to make an example of that. So I'm going to put in a curve, another curve. Is any of these relying on? No. So I'm probably going to, okay, and then that's going to be 1, and I'm going to create another one that's going to start at 0, and that's going to be it. I'm going to take the 2 curves, and I'm going to take one here, take the other one here, and then I'm going to sweep over rail. So the rail curve is going to be this one, the sweep profile is going to be that one. Kink type, blah, 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 and let me see which one is the method that we're going to be following. So that should be sweep, create from sweep. Rail, 2. Oh no, maybe this is 2 rails, okay. Wait, can I create from 1? Yeah, rail, the shape, whether it's close, and the tolerance. Rail, shape, close, and tolerance. Rails, shapes, start, end, rebuild, preserve height. Frame type, sweep frame. I don't know what this means. Kink meter type. I don't really know what that means. Actually, how about we move this? We're going to move this here so that it makes a little more sense. Okay. Yeah, why not? So we're going to mimic this one. All right. And then I'm going to start by introducing what we're doing here. All right. and there will be an introduction video. Okay, I think I'm ready. Am I ready? Do I want to start? And I'm going to do the rail. That's going to be S. The rail is going to be S, and then the sweep. The sweep is going to be that. And sweep. Okay. We're going to drop a panel here. I'm going to get that here and here. And I think we should be good. All right. Okay, so I think I'm ready to start. And why not? So I'm going to vector components, and then here we're going to write nerves components, and yeah. Nope. We're okay. Beautiful. So let's get started. And the introduction I will record later. Okay, I need to remember that. Ooh. Can you hear the background noise? You cannot, right? This noise cancelling thing is great. All right, let's do this. Okay, let's get started. So as you probably remember, what I'm going to do is I'm going to continue on this file that I'm working on over the course of the previous exercises and the previous videos, where we're building incrementally all these prototypes in C# scripting for this plugin that we will end up compiling by the end of the series. So I have my previous utility components, I have my previous vector components, you can check those in previous videos, and then I'm going to create a new category, a new group of nerves components. And the first one that I'm going to model is Grasshopper's sweep 1, which is basically a component that creates a surface by sweeping a profile curve, so the shape of the surface, along a rail curve. So a curve that is somewhere and is defining, imagine the motion of that profile curve moving on top of the rail. Okay, if you want to see that in action, I have here two curves. This one is the rail and the other one is the profile. And if I turn them on, you can see that it generates this kind of like winding surface that falls over itself. Okay, so how are we going to model this? Well, what I have done is I have created a C# script component that takes an input called R, which I already rewrote, an input called S for the shape, and then it spits out an output called sweep, which will be the swept surface, right? And I have probably forgotten, so I'm going to do it right now, to type the input. So I'm going to right click on the R, and I'm going to say that this input must be of the type curve, and S, which is the shape, is also going to be of the type curve. All right. And for this one, I'm going to ignore the input M, the meter kink, whatever type that is. And whenever you want to do these things, whenever you want to, for example, create a B-rep from a sweep, the first place to start is, how do I do this in the first place? The first place to start is always going to be the documentation. So if you go here to the Rhino Common and you Google, for example, let's say I want to do a sweep. Let's see where is that? And I can see that immediately I get from the brep class, I get create from sweep methods. I get a bunch of them, which sounds like a good way to start. So I'm going to click on this, and I see that in the create from sweep method, I have several different overloads, which and I have landed on the third one for whatever reasons, search reasons. So I think what I would like to do is I would like to go back a little bit and say, let me go back to B-reps and let me scroll down all the way to create from sweep, which is what I was looking at before. And you see that I have all these different methods, right? So, or if I go back and you can see that I click on brep and create from sweep specifically, you see that I have all the overloads, so all the different versions of the same method that take different inputs. This one is 2 curves, 1 boolean and 1 double, and it looks like this is a sweep one. This takes more, and this is a general 2-rail sweep. This is a sweep 2, a sweep 1. So it looks like there are several different versions of this. And I believe that the one that probably is implemented in the vanilla Grasshopper is going to be this one. It's going to be great from sweep because it has a lot of options and it can take a list of curves as the shapes, which we haven't seen yet, but we will see very soon. It can take the meter type, which was an option, etc. So this is probably the one that lives inside vanilla Grasshopper, but this is a little too complex. It has a lot of stuff, so I don't think we're there yet. So I think for this example, I'm going to go back to the simplest one, which is a sweep one that takes 2 curves. It takes the rail, it takes the shape, it asks whether if it's close or not, and I may want to add this as an option, and the tolerance, okay? And as you can see, it's a static method, so I need to call it from the brep class itself. We've seen this in previous videos, and it's going to give me back not one brep, it's going to give me an array of breps, which is kind of strange. Why is that? Turns out that sweeping is a complex operation, and depending on the rail curves and the shape curves, etc., the operation may not be just like one clean surface. There might be instances where, because of the kinks or because of other situations, the result is a collection of surfaces. And that's why we will be getting an array of breps here. So let's try this one. So what I'm going to do is I'm going to go to my C# script component. I'm going to write 2 sections here, the algorithm and the outputs. And you already know that I like making this distinction just because it creates cleaner code for my taste, right? And then what I would like to do is I would like to explore the method that we just looked at. So because it's a static method, we say we're going to find it from the brep class itself. So I type brep dot, and you can see that I already get this autocomplete, and I'm going to scroll all the way down to create from sweep, and you can see that here it tells me that there's 5 overloads, right? So I'm going to create from sweep. I'm going to open here, and I'm going to take a look and use this first overload. So it's going to be, the first parameter is going to be the rail, which is coming from the input R. The second is going to be S, which is also coming from the input. Then whether if it's close or not, for the time being, I'm just going to hard code it as a no, but I think I'm going to add that as a parameter. Why not? And then the tolerance, as we have seen in previous videos, we still don't know how to get it from the document. So I'm just going to hard code a 0.01 number. Okay, so that's great. But we'll see in videos, in further video, how to get that tolerance. And then, but I am creating this sweep here, but I need to keep it somewhere as a variable, right? So because we already saw before that the return type is an array of breps, so I'm going to store the result of this operation in a variable of the type array of breps, which I'm going to call sweeps. And that's going to be whatever the return of this method is going to be. Remember from my previous video, this is called the factory method pattern, which means creating new objects instead of using the constructor by using a method that is static and that lives in the overall class. And then the result of this should be that sweep, the output, is going to be equal to all this array of breps that we just calculated. If I hit OK, let's see if it works. So if I turn off this one, you can see that they both overlap. You see that from the preview, it gets much darker. And if I turn this off, you can see that I have here the preview of this one. So it looks like it's working. So just for the sake of completeness, I'm going to add here another parameter called C, whether if it's closed or not. I'm going to right click, type hint, and make sure that it's a Boolean. I'm going to add here a Boolean toggle so that I can turn this on and off, on and off. And then what I'm going to do is I'm just going to remove hard-coded stuff. Hard-coding is not great. If you have the option here and you have the UI, which is so easy to implement, why not do it, right? So I'm going to replace that hard-coded Boolean with with the input. Therefore, now we can say, can I close the surface? Can I open the surface? Can I close the surface? Can I open the surface? And turns out that I'm not really seeing any real change. Okay, so Boolean, we said create from sweep, is it closed? And then let's see, let's write here. Okay, so turns out that even if we turn it on and off, it doesn't really close the surface. So it doesn't wrap it around itself, which I don't know why this is not working. So maybe I'm not understanding well what closed in this kind of parameter means. Only matters if the shape is closed. Okay, so if the shape was already closed, then okay, so maybe we're going to close this one, close curve, all right, and then now this and this and this. I don't see how this makes any difference. Okay, so all right, food for thought. There's something here that I don't know what it means or why is it there or what difference does it make. But we have the option to do that right now. Okay, beautiful. So this was sweeping, creating a B-rep from a sweep between one profile curve, one profile shape, and one rail curve. Okay, what are we going to do? What are we going to try next? And what are we trying to try? What are we going to try next? Okay, so I'm going to say curve divide. Divide curve, that's going to be this one, and it's going to be, for example, a slider here, and K is going to be split segments at the kinks. I don't think we're going to take that right now. Okay, so I'm going to do that, and then I am going to this C shadow component is going to be C, and it's going to be N, and this is going to be oopsie, sorry, this is going to be P, the points, and T is going to be the tangents. Is that what we're doing? The tangents, and lowercase t is going to be yeah, the parameters. All right. Okay, that sounds good. I'm going to just paste it. I'm going to internalize this data. Okay. All right. And this one is going to be super interesting because we're going to do this. All right. The next one we're going to try is going to be taking a curve and dividing it into a set of points at equal relative distance in those points, in that curve. And I really like this one because this one is going to be super representative of the way we typically write C# code in Rhino Common. It has a lot of the patterns that are typical to Rhino Common. So I think this one is going to be great, and it's going to involve a little bit more of code, just not like one line like we're doing with many other components. So let's give this a try. So I have gone ahead and created a prototype of the C# script component, which takes the curve, and I forget I need to type it. So I'm going to right click on C, and in this one is going to be of the type curve that you can see right here, okay? And then n, which is the number of subdivisions, is I'm going to right click and make it an integer because it cannot have a decimal part. I have created outputs P, those are going to be the points, the subdivision points. I have created output T, those are going to be the tangent vectors at the division points, and T, are lowercase t, are going to be the parameter values. What that means is that this is going to give us the value of the parameter. So remember that sort of relative distance along the curve at which these points are going to be found. Okay, so I'm going to drop here a couple panels just to make sure that we can see the information that is coming out clearly. So that's going to be the points, that's going to be the vectors, and that's going to be the parameters. Okay, and why not? Should we just do it here as well? Vectors, the points, the vectors, and the parameters, and these panels are really not great. So sorry for sloppy design. Oh my god. Okay, you see, I should be doing these things offline and not recording. So here, points, vectors, and parameters. Okay, and I'm going to plug in this one here, and I'm going to use this other slider over here. Okay, so I think we're ready. We have the scaffolding. This is going to be divide curve, and I'm going to drop the paint bucket to see the name on it. And I think I'm ready to start figuring out how do I write the algorithms that is going to give me the points, the vectors, all that stuff that I'm going to output from this component. So what I want in general terms is to subdivide a curve in equal length segments. So how could I do this? Well, if I knew nerves and I knew all the math behind it, I could probably pull it off. But as we discussed, that's kind of tricky. And that's why Rhino Common is so powerful. And that's why we use Rhino. So let's see if there's something inside of Rhino Common that gives us that functionality. My intuition is that it would be somewhere along in curves or in the curve class. But I'm just going to start by searching something. So I'm going to say, for example, divide, or I could have typed division, maybe it works, but I can see right away that the first methods that are coming up is on the curve class, there's a method called divide by count, which sounds very promising, which is great. So I can see that there's two methods. So curve.divide by count, and there are one takes a number and a boolean, and the other one takes a number, boolean, and an array of points. This one divides the curve into a number of equal length segments. So let's take a look at the first one. The first one takes the number of segments, takes whether we want the ends or not as a boolean, and returns an array of doubles, which is strange because we want points, right? So what does that mean? It means that the return is a list of curve parameters at the division points, which means that what this component is giving us is not the points themselves, but it's actually those parameters, those relative lengths, if you will. It's not exactly that, but those relative lengths along the curve at which those points are to be found. It doesn't give us the points right away. So but that is great because, first of all, that is something that we already needed to output because we have the output t here, so we needed to find those parameters anyway. And what we can do also is we can use those parameters to figure out then to query, to ping the curve and start getting points one by one based on those parameters. So let's see how that works. So what I'm going to do is I'm going to say first, find parameters for divisions. So what I'm going to do, oh, and something very important, you can see that this method is not static. This is not a static method. It is actually an instance method. So, and you can see also that because I don't have the S icon here in the documentation, and I don't have the static word here on the method declaration. What that means is that I'm not going to write curve dot divide by count. I'm actually going to use this method on the actual curve that I want to divide in segments. So remember, again, this is the difference between using static method and using instance method. This one is an instance one. So what I do is I say, first of all, let me define an array of doubles that I'm going to call parameters. And this is going to be equal to whatever the function returns. So that's going to be on the curve, which on the curve that I want to subdivide, I'm going to press C dot, and then I'm going to start divide by count. And you can see that I just found that method that I was looking at in the documentation. I'm going to open parentheses, and here I have, what is the segment count that I want? Well, that's going to be the input n that I have on the component already. And then the second thing is whether if we want to include the n's or not. We typically want to do that, so I'm just going to hard code a true here. Okay, beautiful. So if I do that and I output on t, on lowercase t, I output parameters, I can already start double checking if my algorithm is going well or not. So I don't have points, I don't have anything, but you can see that the parameters 0, 2.2, 5.3, 11.03. So these are matching my implementation and the original vanilla Grasshopper one. So it looks like we're on a good track. So what that means is that now that I have the parameters, I have to find those points on the curve. So let's go back to that. Find parameters for division. And now find points for these parameters. So the way I'm going to do this is that I'm going to create an array of empty array of points. I could also do a list, it doesn't really matter. And then one by one for each one of these parameters, I'm going to get the point on that curve that corresponds to that parameter. And then I'm going to store it in that array. So I'm going to create an array of point3D objects. Okay, so that's going to be called points, and it's going to be a new array of point3D objects. And remember that when we work with arrays, we have to define the size of the array when we create it. So the size of the array is going to be equal to the size of this other array, because we're going to have equal number of parameters than points. So that's going to be parameters.length. So this array is going to be initialized the same size as however big parameters is. And then with a for loop, so for int I equals 0, I is less than parameters dot length, and then I plus plus. So what I can do now is I can say, well, let me take the parameter. I'm going to call it p. I would typically call it lowercase t, but since I already have that as an output name, I'm not going to do that. So I'm going to take that parameter. So that's going to be parameters I. This is a little redundant to do, but when I teach these tutorials, I like to be a little verbose and like as explicit as possible with things. I'm going to take the value of the parameter. And then what I'm going to say is, now I need to find a point at that curve at this particular parameter. How can I do that? Well, you can probably figure out that that's probably going to involve also working with the curve. So if I go to curve methods, and if I go to all the methods that are available, or if I go to the curve class in general, I can see that I have all the constructors, all the properties, the degree, whether if it's closed or not. And when I get to the methods, if I scroll all the way down, there is a method that is called point@. Let me see if I can find it. And point@, evaluates a point at a curve parameter. And if I click here, you can see that what's interesting is that this method, which is not static, it belongs to particular instances of curves, given a parameter t that I want to evaluate, returns a point 3D object. So this is going to be super straightforward. How did I know this was the one? Well, I have some experience, I've worked this before, but otherwise I could have said, for example, curve point. That's what I'm going to Google. And then you can see that curve, create blend, curve, polyline, curve methods. Maybe this one was not so straightforward to find, but there will be maybe, but finding this and reading through the documentation, I think is a very healthy thing actually at the beginning. Also, I will talk about very soon on the next video, actually, I will talk about another method that I would like to invite you to use if you want to learn how vanilla Grasshopper components work internally and which Rhino common functions they use. Okay, so we're going to use point at on a particular curve. So you can see that now I can say I'm going to declare a variable that I'm going to call pt, and that's going to be for the curve C. I'm going to type dot and I'm going to type point at, which is a method that lives in this particular curve. And I'm going to give point at, I'm going to give it p, which is the parameter that I just got from the array. And the return is going to be that this point is going to be the point that lives at this particular parameter along the curve. And now what I can just say is on the array of points at position I would like to store that object pt. All right, just as simple as that. How can I verify if that works? Well, on the outputs, I'm going to say uppercase P, that's the output of the component. I would like that to be the array of points that I just calculated over here. And if I do that, I'm going to click OK. And you can see that numerically, these two lists actually match really well. So if I turn off one or the other, they're both overlapping. So it looks like we are on good track. So hooray, we now have the points that we have divided from the curve. And last but not least, we need the tangent vectors. So what are we going to do? We're going to follow the exact same pattern here. We're going to find the points for these parameters. So what I could do is I could do the exact same thing. I could create here a vector 3D array of vectors and then write another for loop, take the parameter, find somehow the tangent at that parameter and store it in the array. But since I already have the for loop here, why not do both things with the same for loop? So what I'm going to do is I'm going to find points and vectors for those parameters. So what I'm going to do is I'm going to create here a new array of vector 3D objects. So that's going to be tangents and tangents. And that's going to be a new vector 3D array with this same length. So that's going to be the length of the array parameters. And then in the same for loop, we are going to find the parameter, we're going to find the point, and then over here, I'm going to say, I need now to find the tangent vector. Okay? Same thing. Where is that? How do I do that? I think at this point, I'm going to try, instead of going to the documentation, I'm just going to try to use autocomplete to see if I can find something that sounds well to me. So I'm going to say, I want a vector 3D. Okay? I'm going to call this V, and I'm going to say C dot. And I could start looking, is there something tangent, 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 tangent? Maybe I scroll down all the way to T, R, S, T. Oh, look at this, tangent at, and it takes a double as a parameter, which is great. So this sounds actually very similar to point at. There's another method called tangent at. So this looks great. Let me double check that on the documentation. So I'm going to go to curve. Nope, I'm going to go to curve methods. I'm going to go from here, Rhino geometry curve, the curve class, and I'm going to try to find tangent at. That's a property at the beginning, at the end, And then this is the method, which I can see is not a static method, it's an instance method. And then here, as I click, yes, it returns a vector 3D, it needs a parameter for evaluation. This method looks great to me. So let's use that. So tangent at, and then I'm going to do P, and then tangents at position I is going to be that vector that I just created. Obviously, you can see how you can shorthand these two lines into one. You can just say points at the I position is going to be this thing, and you can save yourself a little bit of code. But again, I like to be a little verbose here so that we can really see what's going on. And then uppercase T is going to be tangents. Is this going to work? Oh, something doesn't work. What's the error? The type space vector D3D, vector D3D. All right, so I have a typo, which is the vector D3D. All right, so that was a typo. I'm going to do that. And tangents, ooh, they look the same exactly. Hooray! So that works. That works. So we now have a component that we can use to take a curve and subdivide it. All right? Beautiful. Now, I know what you're thinking. So I did, I oversaw a tiny detail that might be interesting for us, which is the following. When I was looking at documentation, I was looking at the divide by count method, and let's take a look at that method again. So I'm going to say divide by count, and you can see that there's two methods here. You see there's a method called divide by count. That's the number of divisions and the Boolean. This is the one that we use to include the ends. But there was another one here, which took the number, an integer, a Boolean, and an array of points. What is that? So let me click over here. This one, divide by count method, what this one does is that it divides the curve into an equal length segments, and it's very similar to the previous one. It's also not static, it's an instant method. It returns the array of doubles. It takes the segment count, whether it includes the end, but it has an additional input, which is the subdivision points, a list of division points. And you can see that it has the out parameter, which means that if I give it an empty array, it will fill in that array with points. What? So I had to do a for loop to find those out, but there was a method that already gave me that information. Well, it turns out that there was, but I just wanted to walk through this process because I thought it was pretty healthy now that we're starting to learn how to use these things. But it is true that there was a version of the method that already gave me all these points. So, I mean, it doesn't matter. We used one or the other, but I'm going to teach you as well how we could rewrite the code to use this method instead. So what I'm going to do is, this was the previous version where we explicitly took all those, all the parameters and found the points using the parameters. What I'm going to do now is I'm going to remove all the point stuff, okay? So for the for loop, I am going to only use, actually, wait, so let me just, actually, I'm going to comment this out, okay? And then what I'm going to do is I'm going to rewrite it over here. And so I'm going to uncomment this, and I'm going to say first find parameters and points for divisions. We already saw, if you remember, how in order to use the output, what I need to pass here is an empty array that I generate beforehand. So what I'm going to do is I'm going to say, I'm going to create a variable called points, which is going to be an array of point 3Ds. Okay? And then what I'm going to do is I'm going to pass that array to the out parameter so that the method takes this empty array and fills it in with those points on my behalf so that I don't have to do it myself manually. And I'm going to comment this out so I don't get an error. And then let's see if this works. This, I believe it works like a charm. So I'm getting already the results. And you can see that I have saved myself a lot of code, for loops, etc. Even though probably what happens is that instead of doing it here, the for loops are happening now inside the method. But regardless, it's a little cleaner in my case. And now what I can do is I can take a version of this and I can adapt it so that I only get the tangent vector. So I'm going to uncomment this, and because it's, I don't want to manually remove the tab, so I'm just going to press OK, and it's going to come back perfectly aligned now. And I'm going to remove the line for the points. I'm only going to keep the tangents, and I'm going to remove the lines where I find the points, okay? And so for this one, now the for loop is only for finding the tangents. So I get the parameter, I find the tangents, I store the tangents in the array, and then I spit those out through the output of the component. And then I have the two outputs here, and still the same method, still the same way of doing it. It's just that it's a little bit shorthanded because we had that possibility with the divide count method. Question you may have, well, can I also save myself doing this and just like out here a vectors array of something like that, the tangents? Well, unfortunately not, because since we don't have the capacity to modify Rhino Common, there's no method in Rhino Common that also allows me to pass in an array of vectors. So that part, the tangent part, I need to do it manually myself. Okay. All right, beautiful. So I thought this was actually a really interesting example. So, and very illustrative of a lot of Rhino Common ways of things. So this idea of finding parameters along the surface or the curve, and then using those parameters to get information from the NURBS object is actually a really, really common pattern inside of Rhino Common as well. We're going to see that again when we take a look at the next component, which I believe is going to be taking an UV surface and then finding points and normals and tangents along that surface, which is also an extremely common operation to do. Let's take a look at that. I need to go to the restroom. Hi, CJ, how you doing? I'll be right back. Can you give me a minute? Hello, I'm back. How are we doing here? All right. Okie dokie. I need to double check something. What's going on here? Okay. All right. Okay. So what is next? We're going to use the same thing, the same method, but we're going to take a surface and we're going to subdivide it in UV points. So we're going to evaluate a surface. So I'm going to make that here, and we're basically going to replicate this component. Surface to subdivide, number of segments, these are the points, these are the normals, And this is the parameter coordinates as division points. I think this component is going to be great. So for that, we need a surface, which I'm about to draw. Am I drawing a surface? I am probably drawing a surface. That's happening. Yes. Woohoo! I'm going to draw a napkin of sorts. Yep. I feel like I always draw the same kind of surface. And I'm going to sweep it, I guess. I'm going to sweep this is the rail. No, sorry, this is the rail, and this is the surface. And it's going to look something like that. Huh, okay. All right. This sounds good to me, I guess. Looks a little crumbly. I wonder. It's fine. Yes, it's fine. All right, and this is going to be the surface, which is going to look something like this. I'm going to take the surface here. I'm going to, you see, I actually like that it's crumbly because it shows the offset of UV. That's kind of nice. And this is going to be 10, and this is going to be another 10, and 5 subdivisions, for example, or 4 subdivisions, whatever. 10 and 10 is fine. And we're going to get the points as one list. We're going to get the vectors as another list, and the UV coordinates. And the UV coordinates, exactly. I think this is going to work great. And then here, this is going to be divide surface, the bucket, and then S, and U, and V, and then P, and then this is going to be N for the normals, and then UB, lowercase, S, and U, and V. Now I'm going to copy this over here. And we're going to have here, and here, and here. Okay. How's everyone doing? Okay. All right, so the next thing I need to do is, first of all, figure out how to do this, which I kind of forgot. brep methods, point, is there a point at? Evaluate. Huh. Okay, so what about surface? The surface method, there's surface, point at, okay. Evaluate a point at a given parameter. Sounds good. U and V. Point at, normal at. We get the U and V, so that's great. And that's all I need, really, right? So I can probably do this. the surface point at. Set domain. Set domain. So this is great. Okay. All right. So I think this is what we're going to be doing. Okay. As I said before, I think this idea of finding or generating parameters along a particular nurse object and then querying that object, so a curve, a surface, whatever, and get information at that parameter location, that pattern is so important and is so common in Rhino Common and in nerves modeling in general that I would like to do another example of that. So for the next example, what we're going to do is we're going to replicate the divide surface component, which takes as an input, takes some kind of surface. So for example, this surface that I have here, it takes how many subdivisions in the U and the V direction we want to have, and then it spits out the points on top of the surface. It spits out normal vectors, so perpendicular vectors on that surface, and it spits out the UV points at the UV location where those points are. So basically, just instead of one parameter, it gives me the two-dimensional parameter, the U parameter and the V parameter of all those points. You may also notice that the original component spits out data trees. We don't know how to do that yet. It's going to come in farther videos than this series. So I'm going to replicate this component only using one list after the other. And then in further videos, we will go back and we will modify this component to actually make it output a full-fledged data tree. Okay? So I have gone ahead and created a surface, a bunch of sliders, a C# script component that I have renamed to divide surface. I created inputs for S, U, and V, but I haven't typed them. So I'm going to right click on S and make sure that the type of this is going to be surface over here. And then U and V, because they are subdivisions, are going to be integers. So I'm going to type both to be integer types. And then my outputs are going to be P, which is the number of points, and the normals, and UV are going to be the parameter locations at those points, which I'm going to represent also as points, not points in world coordinates, but points in parameter space. So how am I going to do this? I'm going to double click as usual. I'm going to come here. I'm going to drive my algorithm here and my outputs here. Okay, beautiful. Let's get started. And now let's do some thinking before we get started, because otherwise I'm going to start rambling, blah, 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 and it's not going to be great. Okay. From surface. how am I going to do this? We're going to start by computing the parameters, okay? We're going to start computing the parameters. And then outputting those. And once we have them, we will ping for points and we will ping for the normals. I think that's going to be the easiest way. The first thing that I would like to do, probably as I did before with the curve, is that I would need to find where all those parameters along the surface are, the subdivision parameters that divide the domain of the surface at equal intervals. First, I would like to figure those out, and then I would then like to use those points as those parameters as the place where I want to query, where I want to ask the surface to give me points and to give me normals. So I wonder if there's anything similar to what I did before, where I took the curve and I divided by count. I wonder if there's something similar for the surface. So the first place to start is going to be on the documentation. I'm going to go to the surface class and I'm going to take a look at what's available over there. So you can see that I cannot create surfaces with constructors, as we discussed before. There's a lot of properties. So is it has a B-ref form? Is it solid? Is it valid? And etc. And then we have a lot of methods that are interesting. So we have closest point. We can create extrusions. We can create periodic surfaces. We can find the curvature at a particular UV coordinate. This might be interesting. We may actually want to generate this, spit that out. We're actually going to spit that out also, because why not? We already have that. Then we can get the degree, we can get the domain, we can evaluate a surface mathematically. I'm actually not clear with that. Evaluate, it gives us UV, number of derivatives, and it gives the derivatives. This is kind of interesting. So it gives us a lot of information about the surface at that point. We have frame at, this is going to be a plane. We can get the bounding box. We can get, for example, whether if it's periodic or not. We can get the normal at a particular UV coordinate. We can get a point at a particular UV coordinate. Let's take a look at these two. Point at U and V. We can get the normal at U and V. It looks like these ones are going to be super useful for us farther down the road. But as we can see, we don't really have a division or divide by count method like we had before. I'm actually going to search Control F. I'm going to search dv, and I can find it divides the surface in two parts, but that's splitting. It's kind of like giving me two surfaces, not giving me UV coordinates. I'm going to keep searching, but this is the only match that I have. So it turns out that for surfaces, there's no method that is so clean and so straightforward and giving us the subdivisions. So looks like we're going to have to do this manually, which I also think is an extremely interesting exercise to practice the things that we have learned. So what does that mean? What it means is that what we're going to have to do is to manually figure out the subdivision parameters in both directions at regular intervals. So if we want to divide the surface in one direction at 5 intervals, we're going to have to figure out in that direction, we're going to have to figure out 6 parameters, because it's 5 subdivisions, so it's 6 parameters, 6 subdivisions that are equally spaced along the domain in that direction. So if the domain was from 0 to 1 in that direction, the parameters would be 0, 0.2, 0.4, 0.6, 0.8, and 1, right? So we subdivide the domain in equal parameter spaces. But as we discussed before, surfaces rarely have a clean domain that goes from 0 to 1. That's not typically the case. We could reparameterize the surface and force that domain to be 0 to 1, which will make things cleaner, but then we will not be able to spit out to output just a nice set of parameters like the original component does, working on the domains of the original surface. So we're not going to reparameterize, so we're going to do it the hard way, which is figuring out the domain in each one of the directions, then subdividing that domain in equal parts, and then figuring out each one of the UV components numerically. Okay, so it's going to be a little of a numerical exercise, but very interesting nonetheless. So I'm going to go here, and the first thing that I'm going to do is I need to find the direction in the U and V, the domains in U and V. If I'm still in the surface class, if I search domain, you can see that instead of a property, it's actually a method, which is kind of strange. But why is this? It is because it turns out the surfaces have domain in two directions. So this one gives me the direction, the domain in a particular direction. So 0 for the first direction, that's probably going to be U, and 1 for the secondary direction, that's probably going to be V. And you can see that the return type is of the type interval, which we haven't really seen yet. So if I click here on the return type interval, it takes me to the interval structure, which is for representing an interval in one-dimensional space, which is defined by two bounds or two extremes. Now, what is this? Well, it's basically a simple class that Rhino also gives us, which represents something that goes from one value to another value. That's simple. And the properties are you can get the minimum, the maximum, or you can get the lower bound, or you can get the upper bound of the interval. So T0 and T1 will be the first number and the second one number of that interval. Let's see how that works. So I'm going to declare here a variable of the type interval that I'm going to call U domain. And I'm going to say for the surface S dot, I'm going to call the domain method. You can see that there's also another one called set domain. We're going to use that very soon in this video when we reparameterize curves and surfaces. But first we're going to get the domain and in which direction. So I'm going to type here 0 because I want the primary direction too, right? And just to make sure that this is working, I'm going to print to the console uDomain in a string format. So I'm going to call the toString method of uDomain because otherwise I'm going to get an error. So if I do this, you can see that I cannot convert automatically from interval to string. So I'm going to manually say this has to be string here. I'm going to run this code. This works well. And I'm going to plug a panel here. And I'm going to see that the output component. And you can see that the domain in the U direction goes from 0 to 14.17. Does that make sense? It kind of makes sense because you see if I scroll over here, 14.17 is the end value for the first parameter. So that is looking promising. So let me do the same thing for interval V domain. And that's going to be equal to S dot domain in the secondary direction. So that's going to be 1. And I'm going to copy and paste this. And I'm going to print the V domain to the console. And you can see the V domain goes from 0 to 15.22. Is that so? It is so. You can see that on the second column of the UV coordinates, the V coordinate goes from 0 to 15.22. Beautiful. It looks like this is working. So now what we need to do is we need to figure out what is the step size that we want for each one of these. The step size is going to be how long the domain is divided by the amount of subdivisions. So what we can do here is we can say double step in the u direction, or u step, maybe this is better. U step is going to be equal to s dot length. No, there's no length. Wait, so there's, okay, no, not the surface, sorry. U domain dot length. So this tells me how long it is, which is basically doing t minus 1 plus minus t0. So this would be equal to doing u domain t1 minus u domain t0. It's the exact same thing, all right? But I'm going to take that length and I'm going to divide it by how many subdivisions in the u direction. So that's going to be u. And then here, I'm going to do the same. Double v step is going to be equal to v domain dot length divided by v. And I don't know why I removed the printing to the console. That was actually useful, but let me print the step just in case, each one of them, and see if it makes sense. So print u step and print v step. Am I going to get the, I am going to get the string problem. So I'm going to stringify this, and I'm going to stringify this, and I'm going to press OK. And you can see that in the u direction is 2.83. And in the u direction, you can see that the first step is 2.83. That works. And the second one, 1.522. And you can see that these are also 1.522. So things are looking great so far. So now what can we do with this? So what we will need to do is we need to create a nested for loops. So one for loops inside of the other. We have to, and then for it, we use that to generate UV coordinates. So how is that going to work? Well, let's see. Let me create a for loop where I'm going to say for the value of u, no. So I'm going to start with I equals 0. I is less than the amount of repetitions in the u direction. So that's going to be u, the amount of segments, plus 1. Because remember, if we have 5 subdivisions, it means that we have 6 points that define those 5 subdivisions. And then I plus plus. So that's going to be 1. And then the nested for loop is going to be j equals 0, j is less than v plus 1, and j plus plus. And then here you go. So I'm going to add some get domains, and then generate UV coordinates. All right, beautiful. So for this, what we can say is in the parent for loop, the larger one, I'm going to use this to define the U coordinate. So I'm going to define double U is going to be equal to, at every step, the U coordinate of this point is going to be the value for the beginning of the domain. This is typically 0, but it doesn't have to. It could be something else if the surface was trimmed or something like that. So it will be the value at the beginning plus how many steps we are farther down in the geometry times the distance between those steps, so the step size, in the domain space. So that's why U is going to be equal to U domain T0, so that's the initial value of the domain in the U direction, plus however many times we are in this subdivision, so that's going to be I, and then times the step size in the domain space between those spaces. So that's going to be U step. All right. And then here, V is going to be equal to the same thing. V domain dot T0 plus J in this case, because it's the other direction, times V step. All right. If you don't remember, or if you want to learn more about domains and nerves geometry, etc., Please remember to check my lecture videos on my Introduction to Computational Design course at the Harvard Graduate School of Design. If you want to learn more exactly about what this idea of directions, domains, etc. means. Card should be popping up somewhere, links should be in the description, etc., etc. And I have the U and V domains. To make sure that this is working, let me print to the console U and then white space and V. And this one I don't have to stringify because it's also already going to happen automatically here. So as I do this, you can see that I have this thing, this list of UV that looks extremely similar to here, 0001, blah, blah, blah. This looks great. And then this one here is also looking great. You see? So it looks like this is working so far. Okay? The only thing is that I need to be able to output that in something that is not just this list of strings, which is what the output of the console is right now. I need to output in a similar way that the subdivide component does, which is as points. Okay? So what I'm going to do is, in order to store those UV coordinates in something that has order and structure, what I'm going to do is I'm going to use 0.3ds as a way to store that. This can be confusing because if I store this in points, then the U and V coordinates, which are local coordinates on the surface parameter space, are going to become world coordinates, and it's going to show up in Rhino in some world coordinates. But that is only because numerically Rhino thinks that those are points in 3D. But the real meaning is that those are points in parameter space. So it's a little confusing, but we're only interested in their numbers. We're not interested in a world coordinate representation of those parameters. But still, so what I'm going to do is I'm going to create a list of 0.3ds. I could create an array, and the array would be this value times this value, so the grid of points. But I'm just going to create a 0.3d, and I'm going to call UV points, and I'm going to create a new list of blah, 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 and the autocomplete is not working great, and this is going to be 0.3d objects. And then what I'm going to do is that inside of the nested for loop, I'm going to create a 0.3d that is going to be p, and this is going to be a new 0.3d with coordinates u, coordinates v, and coordinates 0. All right? And I'm going to uv points, I'm going to add that point to that list. Again, I'm not really creating points in world coordinates. I'm just using the point class as a way to contain the u and v coordinates in a way that has order and structure. But my intention is not to represent those in 3D, but to just spit the parameters out in an ordered way. So I have that, and then I think we're ready for saying that the output uv, the lower one, the last one of the component right here, is going to be that list of uv points that I just generated. And is that going to work? You see, I'm already getting this distribution of points in the flat world. But again, never mind that, because the idea here is that what we want is a way to store those coordinates. And you can see that these two are actually making total sense. We have points here, points, blah, 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 etc. So this is great. All right. Beautiful. Just so that we're not distracted, I'm actually going to turn off the visualization of this, and I will use containers to show the visualization of the points and the vectors. Okay? Beautiful. What is next? I think we're ready to find the actual points on the surface. Oh, this is taking a long time, huh? But I think this is really important, actually. So yeah, I may just want to talk about that in the introduction, but it's fine. It takes time. It is what it is. It's getting hot here. All right. Beautiful. Finding the points is actually going to be super easy now that we have done all the due diligence at generating the parameters. So it's going to be extremely easy. If we go to the surface, class, we can see that, as we said before, there was a method called point at. Where did we see that? Point at that gives us a 3D point at a particular u and v coordinate on a surface. And there's another method called normal at that gives us the vector 3D at a particular uv coordinate that is perpendicular to that surface. So we're just going to go back here and we're going to take advantage of this nested for loop that is already going through all the uv points, okay? And then we're going to use that here to generate not the UV coordinates, but generate output information, okay? So for example, let me first create a list here of point 3D objects that I'm going to call points. Very original name, okay? And then this is going to be of the type point 3D. And then what I'm going to do is, once I have figured out the UV coordinates, get the point on the surface. And that's going to be point 3D. Point is going to be, excuse me, point is going to be a new, not a new point, sorry, it's going to be at the surface as I'm going to say, can you give me the point at the particular parameters u, the value that I just calculated, and v, the other value that I just calculated. And then once I have that, I'm going to add to the points list, I'm going to add this new point that I just found. Okay, so that's going to be this one. And I don't know why this is happening. Then I'm going to get the normal on the surface. So that's going to be a vector 3D. Normal is going to be equal to s dot and then normal at. And then also I'm going to pass in the u and v parameters. And then I need to generate here a list of vector 3D information. And you see that vector 3D is going to be here and here. And I'm going to say to the normals list, please add this normal vector that I just calculated. And then here I'm going to create UV points. So that's going to be what I had before. Okay. And I think that's pretty much it. So the output P of the component now should be PTS, so that list that we generated here. And the output uppercase N is going to be the list normals, which I also generated just right here. And if I click OK, let's double check. We have this looks very similar. It looks identical to this one. This also looks identical to this one, except for the tree structure, right? But aside from that, we're great. So, hooray! We have been able to generate generate a mirror of the divide surface. Actually, wait, we said we wanted to expand it and also output the curvature. So why not? I'm going to add here a C output, and then I'm going to say get the curvature. And then, so I think this is going to be a double value, which is going to be C, and it's going to be CS dot curvature at, oh no, it's giving me an object of the type surface curvature. What is that? That is interesting. Surface curvature. What? Okay, so let's go to the curvature at. Curvature at returns an object of the type surface curvature, and that is surface curvature data. Oh, which has a lot of information. It contains inside Gaussian curvature, mean curvature, normal curvature, gets point curvature. Ooh, we could have actually gotten the curvature and get normals and points and UV points, and also spit out Gaussian and mean. I actually did not know this. This is outstanding, actually. So can we rewrite this, for example? So can we say that instead of doing this, instead of doing all of this, okay, Control C, can we say, I'm going to generate surface curvature. SC is going to be equal to S dot curvature at coordinates U and V. Okay? And then once I have that, I'm going to say to the list of points, can you add from SC, can you add the point on the surface? And to normals, can you add SC dot normal? And to UVPTS, can you add SC dot UV point, the location of the UV point? This is going to give me an error because if you see here, UV point is of the type point 2D. So this should be changed here to point 2D, okay? But if I do that, this is working, and I actually see no change because it's the exact same thing. So how convenient, there was an object called surface curvature that already contains all that information. Plus for example, I'm going to create here, what is the mean? And so mean is going to be a double, the mean curvature, and the Gaussian curvature is also going to be a double. All right, so let's just do that. Let's create a list of double. So this is going to be means, new list of a double, and then I'm going to copy and paste this, means, and then Gaussians. And it's also going to be a list of doubles. And then to means, I'm going to add SC dot the value of the mean curvature, and Gaussian add dot SC the value of the Gaussian curvature. If you're interested in knowing more about what the mean curvature and the Gaussian curvature mean, go back, please go to that lecture that I pointed at before, where I explained those concepts. And then maybe here this is going to be the M, and then here this is going to be G, all right? And then double click here. I'm going to take here, mean is going to be means, and then G is going to be Gaussians. And let's see if this works. There is some kind of error. So the name Gaussian does not exist. So it's Gaussians. All right, beautiful. And then can I paste a couple components here, panels, and then get the mean curvatures. So that is very interesting. Mean curvature, negative and positive, means concavity or convexity. Well, no, or that was Gaussian. I forget. I actually forget. Gaussian means, no, mean curvature means, I think it means concavity or convexity, and Gaussian meant whether if it was saddle-like or whether if it was hyperbolic. I forget. I have it on my lecture. I look these things up all the time, reading. So great. So now we have this component that is able to take a look at, I'm actually going to write get surface curvature values, and then extract info from the SC object. All right, beautiful. This is the manual form. Okay. All right, great. So this was actually quite interesting, and I just learned myself something. I did not know that there was a surface curvature object that you could use to get all this information. That's actually quite neat. Okay, beautiful. So this video is now getting a little longer than I expected, but I thought this was actually a really good exercise. And again, that is a great pattern that we're going to use. So I just want to finish this video off with 2 or 3 more components, which are going to be reparameterizing a curve, reparameterizing a surface. Those are going to be super easy to do. And then the last one is going to be creating a curve through an interpolated list of points. So let's take a look at those. Yeah, this is getting longer. Anyway, it doesn't matter because I think it's really good knowledge. It's very important. Okay. Reparameterizing. So if I reparameterize this, the division, you see, go from 0 to 1. And can I set the domain? Length domain, curve domain, measure and set, curve to measure to modify, optional domain. Okay. Okay. I'm going to take this, remove all of this, and then we're going to internalize this data. I'm going to delete this. This curve. And I don't, oh no. Okay, so I don't want to actually remove that. Exactly. Okay, so I'm going to internalize this. Okay. And divide curve, can I reparameterize things? Yes. Okay. So I would like to God, okay, I lost it. All right, so I'm going to have this curve. I'm going to get the domain. So I'm going to plug a panel here. That's going to give me the domain of the curve. I'm going to copy and paste the surface. And I'm also going to get the domain of the surface. All right, and you can also see that curve domain, and there's curves. there's actually no component that changes the domain of a surface. Principal curvature is planar deconstruct, etc. Freeform, subdivision, convex. Yeah, there's no such domain. Mm-hmm. Okay. All right. All right. Now it's a long ass video. Okay. So how am I going to start talking about this? So mhm. I'm going to start talking about the domain as a problem and how reparameterizing is very common and how we right click and reparameterize things, but we don't have that option. So, and there's no such component. And I'm going to talk about how the operation is basically setting the domain of a curve or a surface to a particular domain. So, and we're going to do that. So, and actually, could we talk here about polymorphism? Is it a good way? Is it a good is it a good is it a good thing? Let me actually write a let me see if this is going to work. So what I would say is X is going to be geometry base. And then I'm going to take this. So if X type, object type equals Rhino geometry object types. Wait, so object type is of what kind? Rhino doc objects object type. Rhino doc objects object type dot curve then if object type then how did we do this in the Grasshopper sharp? So we could say curve C is X as curve and then C dot domain is going to be equal to a new interval from 0 to 1. And A is C. And then return. Does that work? Does that work? Well, that worked. And otherwise else, if X object type is right surface, this is not, then surface S equals X as surface. This may actually fail. S dot domain, set domain in the 0 direction, new interval 0 and 1. S dot set domain in new direction is new interval from 0 to 1. I'm just trying this and see because I'm not sure. And this is not going to work. Sorry. Okay, and then what about this? It doesn't work because this is actually a B rep. It doesn't work because it's an actual B rep, which is a pain in the ass because then we have to extract the surface and all the ordeal, Rhino, doc objects, object type. It's going to be more problems than I actually want to get into right now. So print is a B rep. And can we pick a panel here? And it's going to be, it's a B rep. Can we still cast it to a surface? S equals X as surface. Okay, this is still work. Print S dot to string. And this should be null, correct? Yes, it's null. So it doesn't work. So I'm not sure then that I want to do this because this is a lot to take in at this point on the series. Is it though? B equals X as B rep, and then surface S equals B dot surfaces dot 0. And then this 0 to 4. Interesting. What do I want to do? I am not sure. Do I want to get into this mess or do I just want to do two separate components, reparameterized curve and reparameterized surface? I don't know, but I need to make a decision. I think this is a lot perhaps at this point to take. Do you think, folks? I think I'm going to make two separate components because this is a lot to take. This is going to be a lot, yeah. So out, not happening. And then going back to what I wanted to show, which is this, and then this, and this, and this, and this here. Okay. All right. So we're going to do two separate components. Now, all right. Let's go back to the video, which is I'll just finish the video saying, I just stopped the video saying that we're going to do reparameterization. So, reparameterization, I'm not even sure if I'm pronouncing this correctly. What does that mean? As we have seen, when it comes to curves and nerves and surfaces in general, the idea is that there's this thing called the parameter, which is bound between two extremes called the internal domain of a nerve's surface. And you can see that, for example, the curve had a domain that went from 0 to 50 something, and we can know that because all the parameters at the subdivisions went ranged between those two values. And for the surface, we can also see that in the UV direction, it had two very distinctive domains. You see from 0 to 15.22 in V, and from 0 to 14 something something in U. And the idea is that this is great and it's fine, we can work with that, but very often, just for the sake of simplicity, we choose to reparameterize these nerves objects, which is basically saying that we choose to shift that domain and to reshape it to be a value that goes from 0 to 1, because it just makes some calculations in life easier sometimes. That is what is happening underneath when I, for example, go to the curve component and I right click and I reparameterize, and you can see that now all the subdivision parameters are going all the way from 0 to 1. And the same goes from the surface. If I reparameterize the surface, you can see that now the subdivisions are going from 0 to 1 in one direction and from 0 to 1 in the secondary direction, which again makes things life easier for a lot of purposes. So what we're going to do is we're going to do two really quick reparameterized components, which are going to take a curve or a surface, and are going to set the domains to 0 and 1. There's nothing really in vanilla Grasshopper. There's no real component that does that because we have the options to reparameterize inputs. The only similar thing that I have found is the component that can set a curve domain to whatever value. And if we choose 0 to 1, then indeed it is as if we were working if we had just reparameterized. But for surfaces, I might be wrong, but I just have not seen a component that can set the domain of a particular surface in either direction. So we're just going to do that. So how are we going to do this? Well, it's going to be super easy. We're going to take, this was a curve, and now I'm going to say, this is a new component. I'm going to change the input. This is going to be C, and I'm going to say reparameterize curve. That is a huge name for a very simple component. And then this is going to be C out. Okay? And the input here is going to be of the type curve. Remember, it's just on my back right there. So curve. I'm going to take this and I'm going to, just to make sure that this is going to work, I'm going to place here the domain to extract the domain of whatever the output here is. And this is going to be extremely simple. So algorithm and outputs. And then what I'm going to do is I'm going to say the object C has a domain. This is a property that is called domain, which, as you can see in the description, gets or sets the domain of the curve. So we can use this to read the domain or to set it, to change it. So if I type domain and I say this is going to be equal to a new interval object that goes from 0 to 1, then I can now say that the output is going to be that curve that I have modified with a new domain. And if I do that, then you can see that now, boom, I have the new domain of my curve. Now, similarly, I could do this. I'm just going to copy paste here. I'm going to change a couple of things. So this is going to be S, the surface. This is going to be S out. And this is probably going to fail now. Exactly. And I'm going to copy and paste this to make sure that the domains get reparameterized. All right. And then I'm going to rename this to reparameterize surface. And I'm going to remember that I need to change the type here. Type hint is going to be of the type surface right there. Okay. And as I go in, I'm going to now remove all this code and I'm going to say that surface, now if I type domain, the domain of surfaces is not a property, it's a method. So it's a function that I need to call and do something with it. There is one that is called domain, which if you saw the description, it gets the domain in one direction. So this is just because surfaces have two directions, as I said before. So we use methods to control, get or set each one of the two. So domain is for reading and set domain is for changing the domain in one direction or the other. So I can say set domain in direction 0 is going to be a new interval that is going to go from 0 to 1. And now s dot set domain is going to, in the direction 1, is going to be a new interval that is going to go from 0 to 1 as well. And s out, the output, is going to be equal to that surface that I just modified here internally. And you can see that now the output of this is a surface, but the internal domain has been bound to 0 and 1. All right. Okay, so this was great. And then what is the last thing that we're going to do as an example for this video? Hey, Kartik, how are you doing, sir? Good to see you. It's been a while. All right, the last thing that we're going to do is we're going to create an interpolated curve. Degree. And this is going to be whether if it's periodic or not. And then the curve, the length, and the domain. So we can do that. Curve, and then length, and then domain, for example. All right. The last thing we're going to do to wrap up this video is going to be to create a curve over that is interpolated over a list of points. Now, I'm going to do this example because I want to give you a teaser of what it means to working with lists of data as an input, which is something that we haven't seen yet so far. But it's going to be a hands-on example and as a teaser of what's coming next in the next couple of videos. So how does that work? We're going to replicate the interpolate curve component, which takes a list of points that I have already selected from Rhino, and they are in this order, more or less, and that creates an interpolated curve through them, a curve that passes through those points. And it has a couple of inputs, so you can choose degree 2, degree 1, 4, 5. You can choose different degrees for the curve, and you can choose whether if you want the curve to be open, periodic, or not periodic. Okay? It also has not spacing, but we're not going to care about that a lot. And the output is going to be multiple. It's going to be the curve that we want to output. It's going to be the length of that curve, and it's going to be the domain of that curve. This is going to be super interesting, so I'm looking forward to this, and I'm going to replicate those panels here to make sure we are mirroring the component correctly. And I'm going to plug in the points, I'm going to plug in the degree of the curve, and I'm going to plug in the Boolean that tells me if this is working, if this is periodic or not. I haven't typed, I'm going to interpolate curve, so that's going to be the paint bucket, and I have all my inputs and my outputs, and I need to type my inputs, which I haven't done yet. So I'm going to do this with you. I'm going to right click on P, which is whether if it's periodic or not, so that's going to be a Boolean. The degree of the curve has to be an integer, okay? And then vertices, the vertices of the curve, which are multiple. You can see that the input is at this point right now is 6 points. We have to type it. We have to go to type hint, and we have to choose point 3D. But there's an additional thing that we need to do, because if we don't do anything, what we can see is that inside the function, the function is taking as arguments the degree, the periodic, all the output, etc., and it's taking one single point, one single vertex. And with one single vertex, we will actually won't be able to create a curve over all those points. And what will happen, and I will explain this extensively, is that because we have 1 point, but we're giving it 6 points, the component will run 6 different times, one for each one of the points. So what we need to do is we need to change the input access here, so that instead of working, I'm going to right click here, and instead of working with items, so with single elements that are coming from the wire, from the list, I would like to access the whole list at once. So I would like to be able to read all the points at once. And you can see that something already happened. You see how the output, instead of being 6 nulls, is just going to be 1 null? That's because the component now only runs once for the 6 points. Again, I'm going to explain this in the next video, but also, and this is the most important part, you can see that the type of the input, instead of being a vertex now, is a list of points, which is neat, all right? So great, so now I have all those points there, and I will be able to work with those to create an interpolated curve. So the algorithm, the outputs, and then let's go to the documentation and see how can we create an interpolated curve. So interpolate, we have point interpolate, we have Hermite surface, Bezier curve, wait. Curve, create interpolated curve. Okay, this is looking great. So it looks like the curve class has a static method called create interpolated curve that takes a list of points. This is an interface for anything that can be iterated over. So this would be able to take arrays, it will be able to take lists, it will be able to take any iteratable structure. And then here we have another one, which is another overload, which is with the points, the degree, and the not style. And here we have another one, which is the points, the degree, the not style, the start tangent, end tangent. However, I cannot really see an overload that gives me a way to make the curve periodic. All right. So how would I actually go about that? I'm going to have to think about that while we're doing this exercise, but let's start by just simply creating an interpolated curve, the interpolated curve here. So I'm going to say curve C is going to be equal to curve dot, because remember the method was static, so I call it from the class itself, and then create interpolated curve, and then here the points I'm going to be given is v, and then the degree is going to be d. Okay. All right, and then I think that should be it. So the output C is going to be equal to that curve that I just created. Okay, and I can see that there is some kind of slight dissonance between the original one and the previous one. I believe that might be because of the knot styling. So let me actually say that the curve knot style has to be right. Oh, and this is what we can use to specify if the curve should be periodic, which is kind of interesting. So let me add here a third. So this is going to be curve knot style. So I'm going to copy this. All right. And then I'm going to copy this and say dot, and then chord. That is what we had. And you can see that all the options, chord, chord square, or uniform, they have the periodic version. So chord is going to be this one. And if I do this, you can see that there's no dissonance right now. So maybe it's not a bad thing to take a look at, to add the K input here. So let's do that. So I'm going to add here K, and that is going to be of the type integer, all right? And then I'm going to copy another slider here, and that's going to be the knot style. The knot style, 1, 2, 3, 1, 2, 3, okay? So that's great. And then, which means that we need to say the knot spacing values are 0, 1. So what we're going to need to do here is we're going to need to check if k is less than 0 or k is greater than 2, then we're going to print invalid knot style. All right, we're going to print that to the console, and then we're going to return so that we don't do anything with this component. We don't know how to generate that error message yet, but we're going to see that also very soon further down in these videos. So if I do that and I press here and I put here in the console, we have invalid knot style. And then if I go down, now it's working. Okay, so that's great. And I had a typo, so that's going to be not. Okay. And then what I need to do now is I need to figure out a way to take that number, the number that was 0, 1, or 2, and turn that number into an enumerator. So this thing here that we can pass on to the function. So let's see how can we do that. All right, I have forgotten. So can we actually just cast this to a curve knot style? So curve knot style curve knot style equals k as, is that possible? It can, because that's not it's a non-nullable type, so yeah, so that's not going to work. So can we cast it this way? Did that work? It looks like it worked, no? Yeah, but we have different curves now. Oh yeah, because we are not using this here. We're not using this. We're still doing chord, so we are still doing curve. All right, yeah. So now, okay, beautiful. Okay, so let me. Okay, so this works. This works here. Chord. And I think I was here. Thank you very much, 52, the Photoshop. I appreciate that. Now, all right, so the way we're going to do this is, okay, so I need to say this in the channel, in the video. If we look at the documentation, we can see that curve not style is an enumerator. And an enumerator is basically integer numbers that have a name to them and that they make easier defining different sets of categories. What that means is that it's just basically given names to integer values. That makes it easier to code. If you want to know more about enumerators, I have a video on my other playlist, Learning C#, card popping up somewhere right now, okay, or description on the link. So what that means is that it's very easy to convert between them by just casting the value of the integer, casting it to the enumerator. So what we can do here is we can say, I want to define a variable that is going to be of the type curve not style, and that's going to be CKS. And what I'm going to do is I'm going to take the value that is coming from K, all right, so that's the integer, and I'm going to cast that to something of the form curve not style. What C# will do is it will take this integer, it will look up the integer in the enumerator, and it will give me back an enumerator with the right form, curve not style, and with the right member value. So, and then if I do this and I substituted this right here, I can now generate the curve and choose the not style. So that's going to be not style 1, 2, and then 3 is not valid, 4 is not valid, and you can see how they both overlap together. There's no dissonance, so this is working great, except for the periodic part. The periodic part is still not working, but what's beautiful about this is that if you look at the enumerator, you can see that there are two versions for each type, uniform, chord, and square root, and then uniform periodic, and chord, square root periodic. And if you look at the values, the integer values, you can see that they are arranged in a very smart way, which is they are in sequence, but all the periodic versions are 3 units bigger, 3 units larger than their non-periodic version. So what that means is that before we generate the curve not style, what we can do is we can say, if the user is telling me that this is periodic, I need to change the value of K. I need to increase it by 3 units before I convert it to a not style. So let's do that. If P equals true, or we already know that we can shorthand this like this. If P, then I can do is I can say K should be increased by 3 units, right? And then we do the curve not style, we create the surface, etc., the curve, etc., etc. So did that work? True and false. Oh yeah, am I doing the... Did I not? Oh, this is not working. I wonder what's going on. Let me take a look at what's going on. Why is it not working? If P equals true, periodic, this is not kicking in for some reason. Periodic, yes. Periodic. This is what happens when you code so late. Periodic, this is the original. Create interpolated curve, CKS. All right, so let's try something. What if I choose here curve periodic? Oh, I don't get it. Oh, interesting. I get a simple version of this. I don't get chord periodic or uniform periodic. It doesn't close it up. Interesting. Or what if I do square root periodic? It also doesn't close it up. That is very strange. So I'm going to open my cheat sheet here on the side. Which is what I'm going to be talking about. I'm going to open, so I'm going to be showing in the next video. We will do that this afternoon. I'm going to be showing the the Grasshopper Sharp example project, source, curve, spline, and we have primitives here. Yeah. Weird. Huh. Yeah, this is what we're doing exactly. Because we need to duplicate the first point. Oh, God. All right. Okay. All right. Is that the problem? Is that the problem? Periodic, and then v dot add v dot add v0. It is working. Okay. All right. So that was the problem. You need to manually add the last vertex over there. Okay. Okay. Thank you, Grasshopper Sharp. That's why we need to. That's why this project is worth $1 million. Okay, I'll talk about it actually in the next video. So let me finish this off. All right. Yes, so I remember the problem. The problem was that it is true that we have to modify the enumerator and turn it into the periodic form, but at the same time, there's something else that we need to do, and it is that in order to be able to properly close the curve, we need to duplicate the first vertex and put it at the end of the list, so that the last vertex of the curve becomes again the first one. So if P is periodic, what we can do is we can say to the list of vertices V, I'm going to add the vertex that was first on the list, and that's going to be V at position number 0. So with that, I'm duplicating it, and then if I do that, then you can see that now the curve properly closes upon itself, and now it's open, and now it's closed, and these are the different chord types and spacings, etc., and the different degrees of the curve. So it's looking great so far. Periodic planar curve. The only thing that we need to complete is adding that the length output L is going to be equal to C dot and length. But curves don't have a length property because the length needs to be computed. So we can do that by just using the get length property method. Sorry. And then for the domain, for DOM, we can see C dot domain, and that is indeed a property. So that is fine. And then we get the length here, we get the domain, and I think with this we're pretty much done. Hooray! So that was quite a thing. I think this video came out quite lengthy at some point. And it was just, what did we do? 6 components. Okay, so why did it come out so lengthy? Well, I think I really wanted to go into the details of many of the things that were going on. I thought that all this idea of using parameters, querying, surfaces, curves, etc. is actually quite important to learn when using Rhino Commons, and that's why perhaps I think I took a little more extra time. I hope this was useful. I hope this also raised some awareness about how useful and how important and how much power we have with Rhino Common, how great it is to work with, and it also raises some gratitude towards the people who made this happen. Okay. Now, with this, I think this was enough to get a glimpse on how do we work and manipulate, how do we create, manipulate, and work with NURBS geometry, so curves and surfaces. And I'm going to stop it here. These are going to be our NURBS components. I will clean this up for the next video. And then I think before we wrap it up and we move on into the next section or the next group of videos, what I would like to talk a little bit is about a couple details that can help us understand better the relation between classes and structs. And I would also like to introduce you to a project that me and some people from the parametric camp community have been working for quite some time already to help you understand better Rhino Common and to especially help you understand how native vanilla Grasshopper components work or are implemented internally. So I will explain that in the next videos. Thank you. If you liked what you saw here, you found it useful, or if you learned anything, maybe you want to consider liking this video, subscribing to the channel, leaving a comment, hitting notifications to know when we go live or when we publish new videos, etc., etc. Thank you very much and see you on the next videos. Alrighty, that was a lot. Okay, so let me clean this up a little bit, turn it into something decent, and there you go. And I'm going to internalize this data, so I don't need this. I'm going to turn this off. NURBS components, beautiful. Okay. Karthik, of course, contributions are always more than welcome. I'm going to be live streaming this afternoon and I'm going to make a small video about the Grasshopper Sharp project. So if you want to contribute, you're more than welcome to go to the repo, read the instructions for contribution, etc., etc. Okay, I will talk about that in a second. Let me record the introduction to the video we just did and we can go grab lunch. Hello, this is Jose Luis here at Parametric Camp and welcome to another hands-on exercise in this series Advanced Development for Grasshopper, where in this one we're going to particularly look deeper into how to create components that create, manipulate and operate with NURBS geometry, which is a higher level, more complex form of geometry. As you know already, we're going to build incrementally on this file of prototypes that we have for the plugin that we're building together, the Parametric Camp toolbox. And for this one, we're going to create 6 components specifically for NURBS geometry. The first one is going to be how to create a B-rep over a sweep by using a sweep, so sweeping a shape profile along a rail. We're going to learn how to take a curve and subdivide that curve into a bunch of points. We're going to learn how to take a surface and subdivide the surface into also UV points. And then we're going to very easily learn how to reparameterize manually curves and surfaces. And last but not least, how to create an interpolated curve from a set of points, okay? Which will also be a small teaser to what's coming next in the series, which is working with lists of data as inputs. This video turned out to be a little longer than I expected, and I guess I went a little deeper into some of the patterns that we have learned and some of the properties of NURBS geometry, and also at how to read the Rhino Common documentation. So I think it's a little lengthier than what we typically do, but I also think that the patterns and what you will learn in this video will be extremely useful if you know where you are when it comes to computer programming, but you're not used to using computer programming for the generation of complex geometry. So I really encourage you to follow this video. Maybe you can scroll through the boring parts, or you can watch the video at 2 times the speed, whatever works for you, okay? Otherwise, I'll see you in the next videos on this series. Let's get hands-on and let's crunch some NURBS geometry components. Yoo-hoo! All right. Okay, so that was great. So I think with that, I'm going to take a break. We are live streaming this afternoon. We're getting back on at 2 p.m. Eastern time, so in 1.5 hours. I'm going to take a break, grab some lunch, chill a little bit, and then we're going to be back and we're going to learn a bit more about all things Grasshopper encoding. Okay? Thank you very much. It was a pleasure, and I'll see you in a bit if you're up for it. Bye-bye.